Imagine you're exploring at the Quantum AI Lab at Google and suddenly you encounter a lock. It's not just any old classical lock though, it's a shiny new and reinforced quantum lock. You try unlocking it with your same old classical key, but it just gives up because it just doesn't have the memory you need to unlock it. No, you need to start thinking outside of Schrodinger's cat jeopardizing box. You need to start thinking quantum. A classical computer uses bits where each bit can only exist in a state of off or on, mathematically denoted to as 0 or 1 respectively. A quantum computer uses qubits, or quantum bits, that follow quantum mechanics, a field of mechanics that describes quantized systems. What are quantized systems anyway? Well, they're physical systems that can represent certain states, but never in between these states. Furthermore, they can represent multiple states at once in a superposition. However, measuring the superposition would collapse into only one state, eliminating all of its quantum properties. Our enduring qubits are actually quantized systems themselves, and we can further describe their superpositions using a wave function. If we examine this representation of a qubit psi represented by this wave function, alpha and beta represent the amplitude of the states that they can exist in, 0 or 1. Amplitudes are slightly different from classical probability as they are represented by complex numbers because they denote both the probability's magnitude and phase, which represents a directional property of the qubit. We can measure the probability of measuring state 0 or 1 by squaring their respective amplitudes. Phases assist in interference, a quantum property which essentially allows us to alter the amplitudes of our wave function to achieve a desired output without actually measuring and collapsing the wave function itself. If we alter the phases so they exist in opposite vector directions, we can essentially cancel out or eliminate certain states from being measured from our qubit. In quantum computing, superposition is extremely important in another concept called quantum parallelism, which takes advantage of the fact that superpositions can represent multiple states at once. What's cool is that multiple qubits can represent a superposed combination of zeros and ones at a rate of 2 to the n states, which can be computed easily under the property of quantum parallelism. If we input these superpositions into a classical function, we'd only require one call of the function, whereas classically, we would have to evaluate each permutation over a number of bits at an exponential rate. This Quantum AI Lab, our quantum law could represent a variety of problems that classical computers just can't solve. However, thanks to our many properties of quantum mechanics, we're more than prepared to break this quantum lock and expand our impossibly wide world of quantum computing.